The world didn't just reset, it exploded into the strangest evolutionary experiment Earth had ever seen. The age that followed wasn't dominated by sleek predators or massive herbivores. Instead, it belonged to terror birds with axe-shaped beaks, whales that walked on 4 legs, crocodiles that galloped like horses, and mammals so bizarre they looked like fever dreams sculpted in flesh and bone. This was the Cenozoic Era, a time when evolution threw out the rulebook and tried everything at once. The creatures that emerged from the ashes weren't refined or predictable. They were wild, reckless, and utterly magnificent. If you think the age of dinosaurs was strange, wait until you see what came next. The walking whales of Pakistan. Evolution has produced some shocking transformations, but few are as mind-bending as the whale that walked on land. Ambulocetus, discovered in the fossil-rich sediments of Pakistan, looked like something assembled from leftover parts. A crocodile's body stretched long, a wolf's legs attached awkwardly underneath, webbed feet that suggested swimming, and a head that belonged to something halfway between a predator and a sea monster. Its name means walking whale, and that's exactly what it was. A mammal caught between 2 worlds, neither fully committed to land nor fully adapted to water. Ambulocetus lived around 50 million years ago during the Eocene, a time when the Tethys Sea stretched across what is now the Middle East and South Asia. The coastlines were warm, shallow, and teeming with fish, making them perfect hunting grounds for an animal willing to exploit both environments. Ambulocetus didn't just wade into the water like a modern hippo, it actively hunted there, using a combination of walking, paddling, and undulating its spine to move through the shallows. Its legs were strong enough to support its weight on land, but they were also positioned far enough to the sides that walking must have been awkward and energy-intensive. The skull tells the real story of how this animal hunted. Ambulocetus had forward-facing eyes set high on its head, allowing it to peer above the waterline while the rest of its body remained submerged. This is the same strategy used by modern crocodiles, and it suggests ambush tactics. The jaw was long and lined with sharp, conical teeth, perfect for gripping slippery prey. Unlike later whales that evolved baleen or complex social hunting, Ambulocetus was a solitary striker. It likely waited in murky water, watching for fish or small land animals coming to drink, then lunged forward with explosive force. Its ears are one of the most fascinating features. Early whales like Ambulocetus had middle ear bones that were still partially connected to the skull, meaning they couldn't hear well underwater the way modern whales do. Instead, their hearing was likely better suited for detecting vibrations through their jawbone, a trait seen in some crocodiles and early tetrapods. This halfway hearing system is another sign that Ambulocetus was still experimenting with aquatic life, not yet fully committed to it. The legs of Ambulocetus were powerful but strange. Each foot was large and webbed, with robust bones that could push against water effectively. But the leg joints weren't built for efficient swimming. They were built for walking. The femur and pelvis were still connected in a way that allowed Ambulocetus to haul itself onto riverbanks or shorelines, rest in the sun, and possibly even travel short distances overland. This dual capability meant it didn't have to choose one habitat over the other. It could fish in the water during the day and return to land at night, avoiding fully aquatic predators while still accessing rich marine food sources. Studies of its spine reveal another key adaptation. The vertebrae show signs of flexibility in the lower back, suggesting Ambulocetus swam by arching its body up and down, much like modern otters or seals. This up and down motion is fundamentally different from the side-to-side swimming of fish or crocodiles, and it became the signature movement of all later whales. Even though Ambulocetus still had legs, it was already developing the swimming style that would define cetaceans for the next 50 million years. The feet themselves are a point of ongoing debate. Some reconstructions show Ambulocetus with fully webbed feet, turning them into effective paddles. Others suggest the webbing was minimal and the feet were used more for pushing off the bottom in shallow water. Fossilized trackways from similar species show clear prints of toes and claws, supporting the idea that these animals still walked regularly. The truth is probably somewhere in between. Ambulocetus had feet versatile enough to handle multiple environments, even if they weren't perfect for any single one. Its size was also notable. Ambulocetus stretched about 3 meters long and weighed several hundred kilograms, making it one of the larger predators in its ecosystem. On land, this size would have been cumbersome, but in water, it provided power. A large body meant more muscle for explosive strikes, more mass to pin down struggling prey, and more insulation for spending extended time in cooler water. Being big wasn't a disadvantage. It was part of the hunting strategy. What's particularly striking about Ambulocetus is how it fits into the larger story of whale evolution. It represents a critical middle stage between fully terrestrial ancestors like Pakicetus, which looked more like a hoofed mammal, and fully aquatic descendants like Basilosaurus, which had nearly vestigial hind limbs. Ambulocetus is the moment when whales were genuinely walking and swimming, living proof that evolution doesn't happen in clean, sudden jumps. Instead, it's messy, experimental, and filled with creatures that look like they shouldn't work, but somehow thrived. Modern whales are so perfectly adapted to ocean life that it's hard to imagine them ever walking. But Ambulocetus proves they did. This creature waded through coastal swamps, dragged itself onto muddy banks, and hunted with a combination of stealth and power that no modern whale could replicate. It wasn't graceful, it wasn't streamlined, and it definitely wasn't optimized. But it worked. And in the warm, shallow seas of the Eocene, that was more than enough. Titanoboas, the snake that swallowed crocodiles whole. In the steaming rainforests of Paleocene South America, a predator ruled that made modern anacondas look like garden hoses. Titanoboa stretched over 13 meters long and weighed more than a ton, making it the largest snake ever discovered. It wasn't just big, it was absurdly, impossibly massive, with a body thick enough to crush a crocodile and a gape wide enough to swallow it whole. This wasn't a creature that needed venom or speed. Titanoboa was a living constrictor cable, powered by pure muscle and an environment so warm and oxygen-rich that gigantism wasn't just possible, it was inevitable. Titanoboa lived around 60 million years ago, just 10 million years after the asteroid impact that wiped out the dinosaurs. The world was still recovering, and South America was a tropical paradise of dense jungles, sprawling rivers, and swamps teeming with life. Temperatures averaged close to 32 degrees Celsius, far warmer than anything in modern rainforests. For a cold-blooded reptile, this heat was perfect. Snakes rely on external warmth to power their metabolism, and in the superheated climate of the Paleocene, Titanoboa could grow to sizes that would be impossible today. The fossils were discovered in the Cerrejón coal mines of Colombia, one of the richest Paleocene fossil sites in the world. The sheer size of the vertebrae shocked scientists when they were first unearthed. Each bone was massive, far larger than any known snake, living or extinct. When paleontologists reconstructed the skeleton, they realized they were looking at something that redefined the upper limits of snake size. The proportions were similar to modern boas and anacondas, meaning Titanoboa was built the same way, just scaled up to monstrous dimensions. Its diet is one of the most debated aspects. Fossil evidence from Cerrejón shows that the environment was full of large prey, giant turtles, crocodilians, and massive lungfish. Titanoboa would have targeted all of them. Its jaw structure reveals it could open incredibly wide, thanks to highly flexible ligaments that allowed the lower jaw to dislocate and stretch. This is a trait all snakes share, but in Titanoboa, it meant the animal could swallow prey as large as a modern alligator. Bite marks and crushed shells found at the site suggest it regularly fed on turtles, using its immense body weight to crack through their armor before swallowing them whole. The constriction method was its true weapon. Titanoboa didn't need to inject venom or deliver a killing bite. It simply wrapped its coils around its prey and squeezed. Each time the victim exhaled, the snake tightened further, cutting off blood flow and preventing the lungs from expanding. Death came not from suffocation, but from cardiac arrest. The heart couldn't pump blood against the crushing pressure. Modern boas and pythons use the same technique, but Titanoboa's size meant it could overpower animals that would be impossible for smaller constrictors to kill. Its head was relatively small compared to its body, but still large enough to deliver a strong bite. The teeth were sharp and recurved, designed to grip rather than tear. Once Titanoboa bit down, the teeth acted like hooks, preventing prey from pulling away, while the coils did the real work. This combination of bite and hold with constriction is still used by modern boas, but Titanoboa perfected it on a scale never seen before or since. The vertebrae also reveal details about how Titanoboa moved. Each vertebra had large, pronounced processes where powerful muscles attached. These muscles allowed the snake to generate immense force with every movement, whether slithering across the forest floor or coiling around prey. The spine was both flexible and strong, capable of bending into tight loops without breaking. This flexibility was essential for constriction, allowing Titanoboa to wrap its body around irregular shapes and maintain pressure from multiple angles. The environment Titanoboa lived in was as extreme as the snake itself. The Serajon Formation preserves a snapshot of a world where rainforests covered much of the equator, and rivers snaked through jungle so dense that sunlight barely reached the ground. The water was warm, slow-moving, and filled with life. Titanoboa likely spent much of its time near water, where it could ambush prey coming to drink or cool off. Its size would have made it a clumsy climber, so it probably stayed on the ground or in shallow water, letting prey come to it, rather than actively hunting. One of the most important discoveries about Titanoboa is what it tells us about ancient climates. The size of the snake is directly linked to temperature. Reptiles can't regulate their body heat internally, so they rely on environmental warmth to stay active. The bigger the reptile, the warmer the environment must be to support its metabolism. By studying Titanoboa's size, scientists can estimate that the average temperature in its habitat was significantly higher than anything seen in modern rainforests. This finding has important implications for understanding how climates change and how life responds to warming conditions. The extinction of Titanoboa is also a mystery. As the Paleocene gave way to the Eocene, temperatures cooled slightly and ecosystems shifted. Prey availability may have changed, or competition from emerging mammalian predators could have pressured the species. Whatever the cause, Titanoboa disappeared from the fossil record, leaving no direct descendants. Modern boas and anacondas are related, but they never reached the same gigantic proportions. The conditions that allowed Titanoboa to grow so large were unique to its time, and when those conditions ended, so did the age of giant snakes. The terror birds of South America. After the dinosaurs fell, South America became an evolutionary laboratory isolated from the rest of the world. For tens of millions of years, it drifted as an island continent, and without large mammalian predators to compete with, birds seized the opportunity. They grew tall, lost the ability to fly, and evolved into apex predators that ruled with spear-made power and beaks, designed like medieval axes. These were the Paraceratherium, better known as terror birds, and they were among the most successful predators the Cenozoic ever produced. Paraceratherium first appeared around 60 million years ago and thrived until about 2 million years ago, spanning nearly the entire age of mammals. They ranged in size from species as small as modern sirrimars to giants like Chalicotherium, which stood 3 meters tall and weighed several hundred kilograms. Their heads were enormous, housing beaks that were sharp, hooked and reinforced with bone. These beaks weren't just for show. They were precision killing tools capable of delivering devastating strikes that could shatter bone and tear through flesh with terrifying efficiency. The structure of the beak is what made terror birds so lethal, Unlike raptors, which use talons as their primary weapon, phorusrhacids use their heads. The beak was laterally compressed, meaning it was narrow from side to side but tall from top to bottom. This shape allowed the bird to deliver powerful downward strikes with minimal resistance. The tip was hooked like a raptor's talon, perfect for puncturing and tearing. Studies of skull mechanics show that terror birds could strike with immense force, using their entire body weight to drive the beak downward into prey. Their legs were equally impressive. Terror birds were built for speed, with long muscular limbs that ended in sharp, clawed toes. They couldn't fly, so they invested all their evolutionary energy into becoming cursorial hunters, animals specialized for running down prey. Estimates suggest some species could reach speeds of 50 kilometers per hour, faster than most mammals of their time. Once they caught up to their target, a single kick could break ribs, and a well-placed beak strike could kill instantly. The hunting strategy of terror birds was likely a combination of pursuit and ambush. Their large eyes suggest excellent vision, and their long necks gave them a high vantage point for scanning the landscape. They may have stalked prey through tall grass or forest edges, then burst forward in explosive sprints. Some species had shorter, more robust beaks, suggesting they tackled larger, tougher prey. Others had slender, elongated beaks, better suited for quick strikes on smaller, faster animals. This diversity in beak shape shows that terror birds adapted to a wide range of ecological niches. One of the most fearsome species was Paraceratherium, the bird that gave the entire group its name. It stood about 2.5 meters tall and had a skull almost 60 centimeters long. The beak alone was a formidable weapon, but Paraceratherium also had powerful neck muscles that allowed it to shake prey violently from side to side, much like modern predatory birds do with captured animals. This thrashing behavior would have caused massive internal injuries, quickly subduing even struggling prey. Fossil evidence shows that terror birds weren't just opportunistic scavengers, they were active predators at the top of the food chain. Coprolites attributed to Paraceratherium contain bone fragments from mammals, suggesting they regularly hunted and consumed other vertebrates. Bite marks on fossilized bones show the distinctive puncture patterns of terror bird beaks, confirming they were capable of breaking through tough hides and even cracking bones to access marrow. Another fascinating aspect is their feet. Unlike most birds, which have 3 forward-facing toes and 1 backward-facing toe for perching, terror birds had feet optimized for running. The toes were short, strong, and tipped with sharp claws. These claws weren't used for grasping prey like a raptor's talons. They were used for traction and stability during high-speed chases. The foot structure resembles that of modern ostriches and emus, which are also flightless runners. But terror birds took the design further with more robust bones and heavier musculature. The size variation among terror birds is also striking. The smallest species, like Glyptodon, stood less than 1 meter tall and likely hunted rodents, lizards, and insects. The largest, like Chalicotherium, had a skull nearly 70 centimeters long and could have taken down prey as large as primitive horses or early camelids. This size range allowed terror birds to dominate multiple ecological roles simultaneously, from small opportunistic hunters to apex predators capable of challenging any mammal in their environment. Their success was partly due to South America's isolation. During the time terror birds thrived, the continent was separated from North America by a sea barrier. This meant large mammalian predators, like cats, dogs, and bears, couldn't reach South America. Without competition from these groups, terror birds faced no serious rivals. They occupied the ecological niche that big cats and wolves fill in other parts of the world, and they did it with extraordinary effectiveness. However, their reign eventually came to an end. Around 3 million years ago, the Isthmus of Panama formed, connecting South and North America. This land bridge allowed mammals to migrate south, bringing with them a wave of new predators. Saber-toothed cats, wolves, and other carnivores entered South America, and began competing with terror birds for prey. At the same time, climate changes altered the landscape, shifting from dense forests to more open grasslands. These combined pressures were too much. Terror bird diversity declined rapidly, and by 2 million years ago, most species were extinct. One species, Titanus, managed to cross into North America during this period, becoming the only Phorus racid to leave South America. Fossils from Texas and Florida show that Titanus lived alongside mammalian predators for a time, but it too eventually disappeared. The last terror birds clung to survival in South America until around 1 million years ago, but they never regained their former dominance. The age of giant predatory birds was over. Paraceratherium, the hornless giant that towered over trees. There has never been a land mammal larger than Paraceratherium. This colossal herbivore stood over 5 meters tall at the shoulder and weighed close to 20 tons, making it heavier than most elephants and taller than a giraffe. But unlike elephants, it had no trunk. Unlike giraffes, it had a short neck, and unlike any rhinoceros alive today, it had no horns. Paraceratherium was a giant built for browsing, capable of reaching high into trees to strip leaves and branches, while standing on legs thick enough to support a small building. This giant lived during the Oligocene, around 30 million years ago, across a vast range stretching from Eastern Europe through Central Asia and into China. The environment was a mix of open woodlands and grasslands, with scattered forests providing the vegetation Paraceratherium depended on. It was a time of transition as global climates cooled and forests gave way to more open habitats. Paraceratherium evolved to take advantage of food sources that smaller herbivores couldn't reach, effectively creating its own ecological niche by being the tallest animal around. The skull of Paraceratherium was long and relatively narrow, with a downward sloping snout that ended in a flexible upper lip. This lip functioned similarly to the prehensile lips of modern rhinos and tapirs, allowing the animal to grasp branches and pull leaves into its mouth. The teeth were adapted for grinding tough plant material, with high crowns and broad surfaces perfect for processing fibrous vegetation. Unlike modern rhinos, which are primarily grazers, Paraceratherium was a browser, feeding on the leaves, twigs, and bark of trees rather than grasses. Its legs were pillar-like, built to support immense weight. The bones were thick and dense, with large joint surfaces that distributed stress evenly. Walking on 4 legs this size required significant energy, but it also meant Paraceratherium was stable and nearly impossible to knock over. Predators of the time, such as early Hyaenodonts and Entelodonts, would have had a difficult time bringing down a healthy adult. The sheer size alone was a defense. Few carnivores could even attempt to attack something so massive. The neck, while not as long as a giraffe's, was still substantial. It was muscular and flexible enough to reach upward into trees, but also strong enough to support the large head. This combination gave Paraceratherium a feeding range that extended from ground level up to 6 meters high, a zone that few other herbivores could access. By feeding at this height, Paraceratherium avoided direct competition with smaller browsers and grazers, allowing it to thrive in environments where food might otherwise be contested. One of the most remarkable aspects of Paraceratherium is its lack of horns. Modern rhinos use their horns for defense, combat, and display, but Paraceratherium had none. This suggests it relied entirely on size as its primary defense strategy. An adult would have been virtually immune to predation, and even juveniles, while more vulnerable, would have been protected by the herd. The absence of horns also meant the skull could be lighter, reducing the energy cost of supporting such a large head. Fossil evidence shows that Paraceratherium had relatively small eyes positioned on the sides of its head, giving it a wide field of view. This lateral vision would have helped it detect predators while feeding, though its size meant threats were probably rare. The ears were likely large and mobile, similar to modern rhinos, allowing it to hear approaching danger even while focused on eating. Its social behavior remains speculative. but the discovery of multiple individuals at some fossil sites suggests Paraceratherium may have lived in small groups. This would have provided additional protection for young and allowed adults to share information about food sources. Modern rhinos are generally solitary or live in small family units, and Paraceratherium may have followed a similar pattern. The extinction of Paraceratherium is tied to climate change. As the Oligocene ended and the Miocene began, the world continued to cool and dry. Forests shrank and open grasslands expanded. Paraceratherium, which depended on tree-based vegetation, found its food sources disappearing. Smaller, more adaptable browsers and the rise of grazing mammals like early horses and antelopes outcompeted it. By the early Miocene, Paraceratherium had vanished from the fossil record, leaving no direct descendants. Andrewsarchus, the wolf with a skull like a crocodile. When paleontologists first uncovered the skull of Andrewsarchus in Mongolia, they couldn't believe what they were seeing. The skull was over 80 centimetres long, larger than any known land predator of its time. It had massive jaws lined with teeth built for crushing, slicing and tearing. Everything about it screamed an apex predator. But here's where it gets strange. Andrewsarchus wasn't a cat, a dog, or even closely related to modern carnivores. It was an ungulate, a hoofed mammal more closely related to sheep and pigs than to any predator alive today. Andrewsarchus lived around 45 million years ago during the Eocene, a time when Asia's landscape was a mix of forests, floodplains and river systems. The climate was warm and humid, supporting diverse ecosystems filled with early horses, tapirs, giant rhinos and primitive primates. Into this world came Andrewsarchus, a predator unlike anything before or since. Its body was likely built like a massive wolf or hyena, with strong legs, a long torso and a tail for balance. But the head was a pure nightmare, a crocodilian skull mounted on a mammal's body. The teeth tell the story of how Andrewsarchus hunted. The front teeth were sharp and pointed, ideal for gripping prey. The canines were large and robust, built to deliver bone-crushing bites. But it's the molars that reveal the most. They were broad, thick and covered in enamel, perfect for cracking bones and shearing through tough hide. This dental combination suggests Andrewsarchus was an omnivore or a scavenger that could handle a wide variety of food sources, from fresh kills to carrion to hard-shelled prey like turtles. One theory is that Andrewsarchus lived near water, hunting along riverbanks much like modern crocodiles. Its powerful jaws would have been perfect for grabbing fish, turtles, and even small mammals that came to drink. The skull's shape, long, broad, and heavily reinforced, could withstand the stresses of biting down on struggling prey or crushing through thick shells. This aquatic hunting strategy would explain why such a large predator didn't need the speed and agility of land-based carnivores. Another possibility is that Andrewsarchus was primarily a scavenger. Its size and bite force would have allowed it to drive smaller predators away from kills, much like modern hyenas do. The thick molars were ideal for breaking open bones to access marrow, a high-energy food source often left behind by other carnivores. Scavenging would have required less energy than active hunting and could explain why Andrewsarchus evolved such a massive skull without the body of a pursuit predator. The fact that only the skull has been found makes reconstructing the full animal challenging. Paleontologists estimate the body based on comparisons to related hoof mammals, suggesting Andrewsarchus may have weighed close to a ton and measured nearly 4 meters long. This makes it one of the largest terrestrial mammalian predators ever, rivaling even the great entelodonts. But without more complete fossils, much about its appearance and behavior remains speculative. What isn't speculative is the jaw strength. Bite force calculations based on skull structure suggest Andrewsarchus had one of the most powerful bites of any land mammal. This would have allowed it to tackle prey or food sources that smaller predators couldn't handle. The jaw muscles attached to massive bony crests on the skull providing leverage and strength for delivering devastating bites. The extinction of Andrewsarchus coincides with climate shifts at the end of the Eocene. As temperatures cooled and habitats changed, large predators faced increased competition and dwindling food sources. The rise of true carnivores, early dogs, cats and bear dogs, may have also played a role. These animals were more specialized hunters, faster and more efficient than the lumbering Andrewsarchus. Over time, the giant ungulate predator disappeared, leaving behind only that single, incredible skull as evidence of its existence. Chalicotherium, the knuckle-walking gorilla horse. Evolution occasionally produces animals so strange that they seem like mistakes, creatures assembled from mismatched parts that somehow function anyway. Chalicotherium is one of those animals. It had the body of a horse, the arms of a gorilla, claws instead of hooves, and it walked on its knuckles like a chimpanzee. It wasn't a predator, wasn't fast, and didn't fit neatly into any modern category. Instead, Chalicotherium carved out its own bizarre niche as a high-browsing herbivore that used its claws to pull down branches and strip leaves in ways no other animal could. Chalicotherium lived from the Miocene through the Pleistocene, spanning a range from Europe to Asia and Africa. It belonged to a group called Chalicotherium, distant relatives of horses and rhinos, that took a wildly different evolutionary path. While horses evolved hooves and speed, Chalicotherium evolved claws and strength. The result was an animal that looked like it had been designed by committee, with each body part borrowed from a different species. The claws were the defining feature. Each front foot had 3 large curved claws that were sharp and strong but completely unsuited for walking. Instead of stepping on the claws, Chalicotherium walked on its knuckles, much like modern gorillas and chimps. This knuckle-walking gait kept the claws off the ground, preventing them from wearing down while still allowing the animal to move efficiently. The hind legs, in contrast, had small hooves, creating an asymmetrical stance that must have looked awkward but apparently worked well enough for millions of years. The front limbs were extremely powerful, with heavy musculature designed for pulling rather than running. Chalicotherium used these arms to hook branches and drag them down within reach of its mouth. The claws acted like grappling hooks, anchoring into bark and wood, while the animal pulled with its full body weight. This feeding strategy allowed Chalicotherium to access vegetation that other herbivores couldn't reach, particularly the high branches of trees and shrubs. The skull and teeth reveal more about its diet. Chalicotherium had a relatively small head with a long, flexible snout that could reach into dense foliage. The teeth were adapted for grinding leaves rather than grasses, confirming it was a browser. Wear patterns on the teeth suggest it processed large amounts of fibrous plant material, stripping leaves from branches rather than cropping them like a horse or deer would. This browsing lifestyle put Chalicotherium in competition with early giraffes and elephants, but its unique feeding method gave it an edge in certain environments. One of the strangest aspects of Chalicotherium is how it sat. Fossil trackways and skeletal reconstructions suggest it could sit back on its haunches, using its tail and hind legs for support, while freeing up its front limbs for manipulating branches. This sitting posture is rare among large herbivores and shows just how specialized Chalicotherium had become. It wasn't built for running or fighting. It was built for reaching, pulling, and processing vegetation in ways no other animal attempted. Socially, Chalicotherium may have lived in small family groups. Fossil sites sometimes preserve multiple individuals together, hinting at herd behavior. Living in groups would have provided protection from predators like saber-toothed cats and hyenas, which were common in Chalicotherium's habitat. The animal's large size, up to 2.5 meters tall at the shoulder, would have made adults difficult targets, but juveniles would have been vulnerable without group protection. The extinction of Chalicotherium is linked to habitat loss. As forests gave way to grasslands during the late Miocene and Pliocene, browsing specialists like Chalicotherium lost their food sources. Grazing animals like horses, antelopes, and bovids thrived in the new open environments, but Chalicotherium couldn't adapt. Its specialized claws and feeding strategy, which had been advantages in forested environments, became liabilities in the expanding savannas. By the Pleistocene, Chalicotherium had disappeared, leaving no descendants. Macrauchenia, the camel with a trunk and backward knees. South America's evolutionary isolation produced some of the strangest mammals ever, but few were as bizarre as Macrauchenia. It looked like someone started designing a camel, then halfway through decided to add a trunk, rearrange the legs, and top it off with nostrils positioned on top of its head. The result was an animal that paleontologists struggled to classify for decades, eventually placing it in its own extinct order with no close living relatives. Macrauchenia was a chimera of parts that shouldn't have worked together but somehow did. Macrauchenia lived during the Pleistocene, around 2 million to 10,000 years ago, across much of South America. It stood about 3 meters long and 1.5 meters tall at the shoulder, similar in size to a modern llama, but the resemblance ended there. Its legs were long and gracile, built for running, but the joints were positioned in unusual ways that gave the impression of backward knees. This actually wasn't the case. The legs were simply structured differently from most mammals, with longer lower leg bones that created an unusual gait. The most debated feature is the trunk. Macrauchenia had nostrils positioned high on its skull, far back from the tip of the snout. In modern animals, this nostril placement is associated with trunks. Think elephants or tapirs. The exact size and function of Macrauchenia's trunk remain uncertain, but most paleontologists agree it had some kind of flexible proboscis. This trunk would have been used for gathering vegetation, possibly for drinking, and perhaps for social communication through touch or scent. The skull structure reveals that Macrauchenia was a browser, feeding on leaves, fruits, and possibly aquatic plants. Its teeth were adapted for cropping vegetation rather than grinding tough grasses, suggesting it lived in areas with trees and shrubs. The high nostril position might also indicate Macrauchenia spent time in water, using its trunk to breathe while wading through rivers or lakes. This semi-aquatic lifestyle would have given it access to food sources unavailable to purely terrestrial herbivores. Recent studies of Macrauchenia's DNA have provided surprising insights. Despite its odd appearance, genetic analysis shows it belonged to a group called Leptopterna, which were native South American ungulates that evolved completely independently from horses, camels, and other Northern Hemisphere mammals. This is a stunning example of convergent evolution. Macrauchenia evolved camel-like proportions and a trunk without any direct connection to camels or elephants. It arrived at a similar body plan through completely different evolutionary pathways. The feet of Macrauchenia were also unusual. It had 3 toes on each foot, each ending in a small hoof. This is similar to some extinct horses and rhinos, but the arrangement was unique to Macrauchenia's lineage. The toes were arranged to distribute weight evenly, allowing the animal to move across soft ground without sinking. This adaptation would have been useful in the wetland environments Macrauchenia likely inhabited. Fossil evidence shows that Macrauchenia lived alongside many other unique South American mammals, including giant ground sloths, Glyptodonts, and toxodonts. It shared its environment with predators like saber-toothed marsupials and terror birds, making size and speed essential for survival. The long legs suggest Macrauchenia was a capable runner, able to escape predators across open ground. The trunk may have also been used for detecting danger through smell or sensing vibrations. The extinction of Macrauchenia occurred at the end of the Pleistocene, during the same period that saw the disappearance of most large South American mammals. Climate change, habitat shifts, and the arrival of human hunters all likely played role. Macrauchenia's specialized body plan, which had served it well for millions of years, became a liability in rapidly changing environments. By 10,000 years ago, it was gone, leaving behind only fossils and the mystery of what exactly it was. Macrauchenia, the camel with a trunk and backward knees. South America's evolutionary isolation produced some of the strangest mammals ever, but few were as bizarre as Macrauchenia. It looked like someone started designing a camel, then halfway through decided to add a trunk, rearrange the legs, and top it off with nostrils positioned on top of its head. The result was an animal that paleontologists struggled to classify for decades, eventually placing it in its own extinct order with no close living relatives. Macrauchenia was a chimera of parts that shouldn't have worked together but somehow did. Macrauchenia lived during the Pleistocene, around 2 million to 10,000 years ago, across much of South America. It stood about 3 meters long and 1.5 meters tall at the shoulder, similar in size to a modern llama. But the resemblance ended there. Its legs were long and gracile, built for running, but the joints were positioned in unusual ways that gave the impression of backward knees. This actually wasn't the case. The legs were simply structured differently from most mammals, with longer lower leg bones that created an unusual gait. The most debated feature is the trunk. Macrauchenia had nostrils positioned high on its skull, far back from the tip of the snout. In modern animals, this nostril placement is associated with trunks. Think elephants or tapirs. The exact size and function of Macrauchenia's trunk remain uncertain, but most paleontologists agree it had some kind of flexible proboscis. This trunk would have been used for gathering vegetation, possibly for drinking, and perhaps for social communication through touch or scent. The skull structure reveals that Macrauchenia was a browser, feeding on leaves, fruits, and possibly aquatic plants. Its teeth were adapted for cropping vegetation rather than grinding tough grasses, suggesting it lived in areas with trees and shrubs. The high nostril position might also indicate Macrauchenia spent time in water, using its trunk to breathe while wading through rivers or lakes. This semi-aquatic lifestyle would have given it access to food sources unavailable to purely terrestrial herbivores. Recent studies of Macrauchenia's DNA have provided surprising insights. Despite its odd appearance, genetic analysis shows it belonged to a group called Leptopterna, which were native South American ungulates that evolved completely independently from horses, camels, and other Northern Hemisphere mammals. This is a stunning example of convergent evolution. Macrauchenia evolved camel-like proportions and a trunk without any direct connection to camels or elephants. It arrived at a similar body plan through completely different evolutionary pathways. The feet of Macrauchenia were also unusual. It had 3 toes on each foot, each ending in a small hoof. This is similar to some extinct horses and rhinos, but the arrangement was unique to Macrauchenia's lineage. The toes were arranged to distribute weight evenly, allowing the animal to move across soft ground without sinking. This adaptation would have been useful in the wetland environments Macrauchenia likely inhabited. Fossil evidence shows that Macrauchenia lived alongside many other unique South American mammals, including giant ground sloths, Glyptodonts, and Toxodonts. It shared its environment with predators like saber-toothed marsupials and terror birds, making size and speed essential for survival. The long legs suggest Macrauchenia was a capable runner, able to escape predators across open ground. The trunk may have also been used for detecting danger through smell or sensing vibrations. The extinction of Macrauchenia occurred at the end of the Pleistocene, during the same period that saw the disappearance of most large South American mammals. Climate change, habitat shifts, and the arrival of human hunters all likely played roles. Macrauchenia's specialized body plan, which had served it well for millions of years, became a liability in rapidly changing environments. By 10,000 years ago, it was gone, leaving behind only fossils and the mystery of what exactly it was. Moeritherium, the swimming pig that became an elephant. Before elephants had trunks, before mammoths roamed the ice, there was Moeritherium, a stocky, pig-sized creature that spent its days wallowing in rivers and chomping on aquatic plants. It looked nothing like a modern elephant. It had a short snout, a barrel-shaped body, and stubby legs that were more suited for paddling than walking. But hidden in its skull were the first hints of features that would eventually become tusks and trunks. Moeritherium was one of the earliest relatives of elephants, and studying it reveals how one of the most recognizable animals on Earth evolved from something completely unexpected. Moeritherium lived around 37 to 35 million years ago, during the late Eocene and early Oligocene in North Africa. The region was vastly different from today's deserts. It was a lush, swampy landscape crisscrossed with rivers and lakes. Moeritherium thrived in these waterways, spending much of its time semi-submerged like a modern hippo. Its eyes and nostrils were positioned high on its skull, allowing it to see and breathe, while most of its body remained underwater. The teeth are what connect Moeritherium to elephants. It had continuously growing incisors in both the upper and lower jaws, early versions of tusks. These weren't the massive ivory tusks of later elephants, but short, stubby projections used for digging, stripping bark, and possibly fighting. The molars were relatively simple compared to modern elephants, designed for grinding soft vegetation rather than tough grasses. This suggests Moeritherium fed primarily on aquatic plants, river vegetation, and soft leaves. The body shape of Moeritherium was compact and heavy, built for stability in water rather than speed on land. Its legs were short and thick, ending in broad feet that helped distribute weight on soft, muddy ground. It likely moved slowly on land but was an effective swimmer, using its bulk to push through water and its feet to paddle. This semi-aquatic lifestyle would have protected it from many land-based predators while giving it access to abundant food. One of the key debates about Moeritherium is whether it had a trunk. The skull shows no clear evidence of the extensive nasal passages that support a long trunk in modern elephants, but the snout was elongated compared to other mammals its size. Most paleontologists believe Moeritherium had a short, flexible upper lip or a very rudimentary trunk. Nothing like the versatile appendage elephants use today, but perhaps capable of basic grasping and manipulation. This would represent an early stage in trunk evolution, somewhere between a normal mammalian snout and the fully developed elephant trunk. The environment Moeritherium lived in was teeming with life. It shared its swampy habitat with early whales like Basilosaurus, ancient crocodiles, and a variety of fish and invertebrates. Being semi-aquatic gave Moeritherium a survival advantage. It could escape into the water when threatened on land and retreat to shore when aquatic predators became too aggressive. This flexibility in habitat use likely contributed to its success during a time when Africa's climate was fluctuating. Social behaviour in Moeritherium is difficult to determine from fossils alone, but modern elephants are highly social, living in matriarchal herds with complex communication. It's possible that early elephant relatives like Moeritherium exhibited some degree of social behaviour, perhaps living in small family groups near water sources. The presence of multiple individuals at some fossil sites supports this idea, though definitive evidence remains elusive. The evolutionary path from Moeritherium to modern elephants involved several key changes. The snout gradually elongated into a trunk. The tusks grew larger and more specialized. The body increased in size, and the legs lengthened to support greater weight. But the basic blueprint, herbivorous diet, social behavior, and adaptability, was already present in Moeritherium. It was the ancestor that set elephants on their unique evolutionary trajectory. Moeritherium eventually went extinct as Africa's climate dried and swampy habitats disappeared. Its descendants, however, diversified into a wide array of forms. Some became the mastodons of Eurasia and North America. Others evolved into the mammoths that would later roam the Ice Age tundra. Still others became the modern elephants that survive today. All of them trace their lineage back to that humble, pig-like creature swimming in the rivers of ancient Africa. Hyaenodon, the dog that hunted like a hyena. Hyaenodon looked like a dog, moved like a dog, and hunted like a dog. Except it wasn't a dog at all. It belonged to an entirely different group of carnivorous mammals called creodonts, which dominated as predators for tens of millions of years before being replaced by true carnivorans. Hyaenodon was one of the most successful creodonts, with species ranging from cat-sized hunters to wolf-sized predators capable of taking down large prey. It represents a time when Earth experimented with different predator designs, and the version we see today, dogs, cats, bears, was not yet guaranteed to win. Hyaenodon lived from the late Eocene through the early Miocene, roughly 40 to 20 million years ago, across North America, Europe, Asia, and Africa. This wide distribution shows how adaptable and successful the genus was. Different species occupied different niches, from small opportunistic hunters to apex predators that competed with early dogs and cats for food and territory. The diversity within the genus means Hyaenodon wasn't a single body plan, but a range of forms adapted to various environments. The skull of Hyaenodon was long and low, with powerful jaws lined with sharp teeth. Unlike true carnivorans, which have specialized carnassial teeth for slicing meat, Hyaenodon's molars were arranged differently. The carnassial teeth, those used for shearing through hide and muscle, were positioned farther back in the jaw. This gave Hyaenodon a stronger bite at the back of its mouth, but made it less efficient at the front. It couldn't bite as precisely as a modern cat, but could deliver crushing force once it had prey firmly in its jaws. The teeth themselves were sharp, blade-like, and designed for puncturing and slicing. Hyaenodon had prominent canines for delivering killing bites, and its molars were perfect for processing meat. Wear patterns on fossilized teeth suggest Hyaenodon consumed entire carcasses, including bones, much like modern hyenas. This ability to process bone gave Hyaenodon access to nutrients other predators might leave behind, reducing competition and increasing survival chances. The body of Hyaenodon was built for endurance hunting. It had long legs relative to its body size, suggesting it could cover ground efficiently. The limbs were digitigrade, meaning it walked on its toes rather than flat-footed, which is typical of cursorial predators. This toe-walking stance increased stride length and reduced energy expenditure during long chases. Hyaenodon likely hunted by pursuing prey over distance, relying on stamina rather than explosive speed. One of the most interesting aspects of Hyaenodon is its brain. Compared to modern carnivorans, creodonts had relatively small brains with less developed cerebral cortexes. This suggests they relied more on instinct and less on learned behavior than modern predators. Dogs, cats, and bears have larger, more complex brains that allow for problem-solving, social learning, and flexible hunting strategies. Hyaenodon's simpler brain may have been a disadvantage as ecosystems became more complex and competition intensified. The extinction of Hyaenodon and other creodonts is linked to the rise of true carnivorans. As dogs, cats, and other modern predator groups evolved, they proved more adaptable, more intelligent, and more efficient hunters. They could learn new strategies, adapt to changing environments, and form complex social structures. Hyaenodon, despite its success for millions of years, couldn't compete. By the early Miocene, most creodonts had disappeared, replaced by the carnivorous ancestors of wolves, lions, and bears. Arsinoitherium, the horned beast that wasn't a rhino. Arsinoitherium looked like evolution tried to design a rhinoceros but decided to make it more dramatic. It had two massive side-by-side horns jutting forward from its skull, like natural battering rams, a bulky body supported by pillar-like legs. and a surprisingly small brain for such a large animal. But despite its rhino-like appearance, Arsinoitherium wasn't related to rhinos at all. It belonged to a completely different lineage, one that evolved in isolation in Africa and produced some of the continent's strangest mammals before going extinct without leaving any descendants. Arsinoitherium lived around 35 to 27 million years ago during the Oligocene in what is now Egypt and other parts of North Africa. The environment was a mix of rivers, swamps, and forested areas, far wetter and greener than the Sahara Desert we see today. Arsinoitherium was well suited to this landscape, spending much of its time near water where vegetation was abundant. Its large size and unique horn structure suggest it had few natural predators, relying on intimidation and size as primary defences. The horns are the most striking feature. Unlike rhino horns, which are made of keratin and grow from the skin, Arsinoitherium's horns were hollow, bony structures that formed part of the skull. They were fused side by side, creating a massive double horn that could span over 60 centimetres wide. Behind the main horns was a second smaller pair, though these were much less prominent. The function of these horns has been debated. Some scientists think they were used for defence against predators. Others believe they were primarily for intraspecific combat, with males clashing horns to establish dominance or win mates. The skull itself was thick and heavily reinforced, capable of withstanding the impact forces generated during horn clashes. The neck was short and muscular, providing the stability needed to absorb shock. Studies of skull structure suggest that Arsinoitherium could deliver powerful forward thrusts with its horns, much like modern musk oxen or bighorn sheep. This combat strategy would have been effective both for defending territory and for competing with rivals. The teeth reveal Arsinoitherium's diet. It was a herbivore with low crown molars suited for browsing on soft vegetation rather than grazing on tough grasses. It likely fed on leaves, aquatic plants, fruits, and shrubs. The position of the teeth and the shape of the jaw suggest it cropped vegetation with its front teeth and ground it with the back molars. This diet would have been abundant in the swampy, river-rich environments where Arsinoitherium lived. The body was massive, but not built for speed. Arsinoitherium had short, sturdy legs and a heavy torso, suggesting it moved slowly and deliberately. It probably spent much of its time feeding in one area, only travelling when food became scarce. Its large size meant it needed to consume huge amounts of vegetation daily, much like modern elephants. The feet were broad and padded, helping distribute weight on soft, muddy ground. One of the strangest aspects of Arsinoitherium is its evolutionary position. For decades, scientists struggled to figure out where it fit in the mammal family tree. It wasn't related to rhinos, despite the superficial similarities. Eventually, studies revealed that Arsinoitherium belonged to a group called Hyaenodon, which also includes elephants, sea cows, and hyraxes. This means Arsinoitherium was more closely related to elephants than to any hoofed mammal, despite looking and behaving nothing like an elephant. The extinction of Arsinoitherium coincides with major climate shifts at the end of the Oligocene. As Africa's climate dried and forests gave way to more open habitats, Arsinoitherium's food sources disappeared. Animals better adapted to grazing, like early elephants and rhinos, thrived in the new environments, while specialised browsers like Arsinoitherium struggled. With no close relatives and no ability to adapt quickly, the lineage went extinct, leaving behind only fossils and the mystery of what might have been. Brontotheres, the thunder beasts with forked noses. Brontotheres were among the largest land mammals of the Eocene, and they looked like someone tried to design a rhino, then halfway through decided to add bizarre forked or club-shaped horns to its nose. These weren't subtle ornaments. Some species had massive, Y-shaped nasal horns that branched outward like antlers made of bone. others had blunt hammer-like projections that looked more suited to demolition than defence. Despite their fearsome appearance, Brontotheres were herbivores, using their strange headgear not for hunting, but for combat, display and competition with rivals. The name Brontothere means thunder beast, coined because Native Americans who found their fossils believed they were remains of creatures that rode storms across the plains. The scientific name for the group is Brontotheridae, and they were widespread across North America and Asia during the Eocene, roughly 56 to 34 million years ago. At their peak, Brontotheres were among the most common large mammals, with dozens of species ranging from pony-sized browsers to giants like Megatherium, which stood over 2.5 meters tall at the shoulder. The horns varied dramatically between species. Early Brontotheres had small, bump-like structures on their noses, barely noticeable. As the group evolved, these structures grew larger and more elaborate. Some species developed paired horns that curved outward. Others had a single, massive fork that split into 2 points. The largest forms had horns so big and oddly shaped that they look fake even in museum displays. These horns were covered in skin and probably had a keratin sheath, similar to the horns of modern cattle. The function of these horns is fairly clear. They were used in intraspecific combat. Fossil skulls show impact damage consistent with head-to-head collisions, and many specimens have healed fractures that could only have come from violent clashes. Male Brontotheres likely fought for mates or territory, locking horns and pushing until one gave up. This is similar to the behaviour seen in modern bighorn sheep, elk and bison. The elaborate horn shapes may have also served as visual displays, with larger, more symmetrical horns signalling health and genetic fitness to potential mates. The body of the Brontotheres was robust and powerful. They had thick legs, barrel-shaped torsos, and relatively short necks. Their teeth were adapted for browsing on soft vegetation, leaves, fruits, and tender shoots. Unlike later herbivores that evolved to process tough grasses, Brontotheres were forest dwellers that depended on trees and shrubs. This dietary specialisation worked well during the warm, forested Eocene, but became a liability as the climate cooled and grasslands expanded. Brontotheres had relatively small brains compared to their body size, even smaller than many of their contemporaries. This suggests they relied on simple behavioural patterns and may not have been particularly intelligent. Their success came from size, strength, and the ability to dominate food resources rather than from behavioural flexibility. When environments changed, this lack of adaptability likely contributed to their downfall. The feet of Brontotheres were also unusual. They walked on 4 toes on their front feet and 3 on their hind feet, a pattern similar to early horses. The feet were padded and broad, designed for walking on soft forest floors rather than hard, open ground. As forests gave way to grasslands, Brontotheres found themselves increasingly out of place. They couldn't run fast enough to escape predators on open ground, and their feet weren't suited to harder terrain. The extinction of Brontotheres happened relatively quickly at the end of the Eocene. A combination of climate change, habitat loss, and competition from other herbivores drove them to disappearance. The rise of horses, rhinos, and early elephants, all better adapted to the new environments, left little room for the lumbering thunder beasts. By the beginning of the Oligocene, Brontotheres were gone, leaving behind only their massive, strangely horned skulls as evidence of their existence. Embolotherium, the battering ram of Mongolia. If Brontotheres were strange, Embolotherium took that strangeness to an extreme. This Asian relative of North American thunder beasts had one of the most dramatic skull modifications ever evolved by a mammal, a massive, hollow battering ram protruding from its forehead. The structure wasn't a horn in the traditional sense, but an enlarged nasal cavity that formed a thick, bony shield covering the front of the skull. It looked like the animal was wearing a permanent helmet, and it probably functioned exactly like one during head-to-head combat. Embolotherium lived during the Middle to Late Eocene, around 40 million years ago, in what is now Mongolia and parts of China. The environment was a mix of open woodlands and river valleys, with seasonal variation that required adaptability. Embolotherium was one of the largest mammals of its time, standing over 2 meters tall at the shoulder and weighing close to 2 tons. Its size alone would have deterred most predators, but the skull structure suggests it also used its battering ram for active defense and intraspecific combat. The battering ram structure was formed by the enlargement of the nasal bones, which ballooned outward and upward, creating a thick, dome-like projection. Unlike the forked horns of some Brontotheres, Embolotherium's ram was solid, broad, and positioned directly over the eyes. This placement meant that when the animal lowered its head, the ram became the first point of contact in any collision. The bone was extremely thick, with internal struts that reinforced the structure and prevented it from cracking under impact. Fossil skulls show evidence of damage consistent with high-velocity collisions. Healed fractures, compressed bone, and impact scars suggest Embolotherium regularly engaged in violent headbutting contests. These battles were probably part of mating rituals, with males competing for access to females. The animal with the largest, strongest ram would have had a significant advantage, able to deliver more forceful blows and withstand harder hits. Over time, this led to an evolutionary arms race, with rams growing larger and skulls becoming thicker. The rest of the body was built to support this combat behaviour. Embolotherium had a short, powerful neck packed with muscles that could generate explosive force. The shoulders were broad and heavily muscled, providing stability during headbutting. The legs were thick and strong, with wide feet that could grip the ground and prevent sliding. When 2 males collided, the impact would have echoed across the landscape, a thunderous crash that gave these animals their nickname. The teeth revealed that Embolotherium was a browser, feeding on leaves, fruits, and soft vegetation. The molars were relatively simple, without the complex ridges seen in later grazing mammals. This suggests Embolotherium lived in forested or semi-forested environments where tender plants were abundant. As with other Brontotheres, the shift to grasslands at the end of the Eocene spelled doom for Embolotherium. Its specialized skull, which had been an asset in combat, became a liability in a changing world where speed and dietary flexibility mattered more than brute force. Uintatherium, the saber-toothed herbivore. Uintatherium is one of those creatures that makes you question why evolution would give a plant-eater saber teeth. This massive herbivore stood over 2 meters tall at the shoulder and weighed close to 2 tons, making it one of the largest mammals of the Eocene. Its skull was covered in bony knobs, 6 in total, that protruded from the forehead and nose like evolutionary decorations. But the real shock came from the canines, long, downward curving tusks that looked more suited to a predator than an animal that spent its days eating leaves. Uintatherium lived around 50 to 40 million years ago across North America, particularly in what is now Wyoming, Utah, and other parts of the western United States. The environment was warm, humid, and dominated by subtropical forests and river systems. Uintatherium was a common sight in these landscapes, lumbering through dense vegetation and feeding on a variety of plants. Its large size meant it had few natural predators, though early creodonts and possibly large crocodiles could have posed threats to juveniles. The 6 bony knobs on the skull are one of Uintatherium's most distinctive features. These weren't horns in the traditional sense. They didn't have a keratin covering and weren't used as weapons. Instead, they were likely display structures used to signal dominance, health, or readiness to mate. Sexual dimorphism in the skulls suggests males had larger knobs than females, supporting the idea that they played a role in mate selection. The knobs may have also supported thick skin or fatty deposits that further enhance their visual impact. The saber-like canines are harder to explain. In males, these tusks could reach 15 centimetres long and curved downward like miniature sabres. They weren't suited for eating. Plant-eating mammals don't need stabbing teeth. Instead, they were almost certainly used in combat between males. Uintatherium likely fought by slashing at rivals with its canines, delivering painful but rarely lethal blows. Fossil skulls show scarring and damage consistent with this kind of combat, with healed wounds indicating many animals survived multiple fights. The body of Uintatherium was bulky and slow-moving. Its legs were short and thick, designed for supporting massive weight rather than running. The feet were broad and padded, adapted for walking on soft, muddy ground. Uintatherium probably spent much of its time near water, feeding on aquatic and semi-aquatic plants. Its low-crowned teeth suggest it ate soft vegetation rather than tough grasses, which hadn't yet become dominant in North America. One of the strangest things about Uintatherium is its brain, or rather, how small it was. Relative to body size, Uintatherium had one of the smallest brains of any mammal, smaller even than the tiny brains of Brontotheres. This suggests it relied almost entirely on instinct, with little capacity for learning or problem-solving. In the stable, predictable environments of the Eocene, this wasn't necessarily a problem. But as climates shifted and ecosystems became more variable, Uintatherium's lack of behavioural flexibility likely became a serious disadvantage. The extinction of Uintatherium came at the end of the Middle Eocene, around 40 million years ago. Cooling climates, changing vegetation, and increased competition from other herbivores all played roles. Unlike horses and rhinos, which adapted to the new grassland environments, Uintatherium couldn't shift its diet or lifestyle. Its specialised body plan, heavy, slow, and dependent on soft vegetation, became a liability. Within a few million years, the lineage was gone. But then, it had another pair of horns jutting forward from its snout, branching upward in a Y shape that looked more decorative than functional. It wasn't a deer at all. It belonged to a group called Protoceratids, North American herbivores that evolved elaborate headgear millions of years before true deer arrived on the continent. Syndyoceras lived during the Miocene, around 20 million years ago, in what is now the Great Plains of North America. The landscape was transitioning from forests to open grasslands, and Syndyoceras adapted to this changing environment. It was about the size of a modern white-tailed deer, with slender legs built for running and a lightweight frame suited for quick escapes from predators. But those bizarre horns set it apart from anything alive today. The horns over the eyes were relatively straightforward, simple, pointed structures that could be used for defense or combat. The nasal horns, however, are a mystery. They branched into a Y shape, with each prong curving upward and slightly outward. These horns were made of bone and covered in skin, possibly with a keratinous sheath. They weren't positioned well for fighting. They stuck forward awkwardly, making them more likely to break than to deliver effective blows. So what were they for? The most likely explanation is sexual selection. In many animals, males evolve elaborate ornaments not because they're useful in combat, but because females prefer them. Bright colours, long tails, and oversized horns can all signal genetic fitness, even if they make survival harder. Syndyoceras's nasal horns may have been a visual display, with males showing them off to attract mates. The larger and more symmetrical the horns, the more attractive the male would have been. This kind of runaway sexual selection can produce traits that seem absurd from a survival standpoint, but make perfect sense in the context of reproduction. The body of Syndyoceras was adapted for life in open habitats. Its long, thin legs were built for speed, allowing it to outrun predators like primitive dogs and saber-toothed cats. The teeth were typical of browsing herbivores, suited for eating leaves, fruits, and soft vegetation. As grasslands expanded during the Miocene, Syndyoceras likely shifted its diet to include more grasses, though it never became a pure grazer like later deer and antelopes. Fossil evidence suggests Syndyoceras may have lived in small herds, similar to modern deer. Group living would have provided protection from predators, with multiple sets of eyes watching for danger. Males probably competed for dominance within these herds, using their eye horns to lock and push, while the nasal horns served as visual displays. Combat between males would have been ritualized and relatively low risk, with most contests decided by posturing rather than actual fighting. The extinction of Syndyoceras and other protoceratids occurred during the late Miocene, as true deer and antelopes migrated into North America from Eurasia. These new arrivals were more efficient grazers, better adapted to the expanding grasslands. Protoceratids, with their bizarre horn arrangements and less specialized teeth, couldn't compete. By the Pliocene, they were gone, leaving behind only fossils and the question of why evolution would ever create something so strange. Procoptodon, the giant kangaroo with a flat face. When most people think of giant extinct animals from Australia, they picture the massive wombat-like Diprotodon or the terrifying marsupial lion. But Procoptodon, the giant short-faced kangaroo, was just as remarkable. Standing over 2 meters tall and weighing up to 200 kilograms, Procoptodon was the largest kangaroo that ever lived. But size wasn't its only unusual feature. It had a short, flat face, forward-facing eyes, and only a single toe on each foot. It looked like a kangaroo redesigned by an engineer who wanted to see how weird a marsupial could get while still being recognizable. Procoptodon lived across Australia during the Pleistocene, from roughly 2 million years ago until about 40,000 years ago. The Australian landscape at the time was a mix of open grasslands, woodlands, and semi-arid zones. Procoptodon was adapted to these dry environments, with long legs built for covering ground efficiently in search of food. Unlike modern kangaroos, which have 4 toes on each foot, Procoptodon had only one large, hoof-like toe. This single toe reduced the surface area in contact with the ground, making Procoptodon's hop more energy efficient, but also less stable on uneven terrain. The flat face is one of the most striking features. While modern kangaroos have elongated snouts suited for grazing on grasses, Procoptodon had a short, deep skull with forward-facing eyes. This eye position is unusual for prey animals, which typically have eyes on the sides of their heads for wide-angle vision to detect predators. Forward-facing eyes suggest Procoptodon had better depth perception, possibly for navigating through forests or selecting specific leaves and branches to eat. The jaw was deep and powerful, with teeth adapted for browsing on tough, fibrous vegetation like shrubs and trees. The arms of Procoptodon were also more developed than in modern kangaroos. It had long, flexible forelimbs with strong clawed hands capable of grasping and pulling down branches. This allowed Procoptodon to access vegetation that smaller kangaroos couldn't reach, giving it a competitive advantage in environments where food was scarce. The ability to manipulate branches with its hands also meant Procoptodon could strip leaves more efficiently, processing more food in less time. One of the most debated aspects of Procoptodon is how it moved. Modern kangaroos use bipedal hopping for high-speed travel, but they can also move slowly on all fours. Procoptodon's single-toed feet and large body suggest it may have been a specialized hopper, unable to move comfortably on all fours. Some scientists think it may have walked more upright than modern kangaroos, using its long tail as a balance aid. This upright posture would have allowed Procoptodon to see over tall grasses and shrubs while foraging, helping it spot predators or find food. The extinction of Procoptodon coincides with the arrival of humans in Australia around 50,000 years ago. While climate change was also a factor, Australia was becoming drier and more arid. Human hunting likely played a significant role. Procoptodon would have been a valuable target for early hunters, large, relatively slow, and unable to hide effectively in open landscapes. Within a few thousand years of human arrival, Procoptodon and most other Australian megafauna were gone. Glyptodon, the armoured tank that roamed South America. Imagine an armadillo the size of a Volkswagen Beetle, covered in a shell so thick that predators couldn't bite through it, with a tail tipped with a club made of solid bone. That was Glyptodon, one of the most heavily armoured mammals ever to walk the earth. It looked like something from a fantasy game, but it was real, and it was remarkably successful for millions of years. Glyptodon's shell wasn't made of flexible bands like a modern armadillo. It was a single, rigid dome of fused bone plates that turned the animal into a living fortress. Glyptodon lived across South America during the Pleistocene, roughly 2.5 million to 10,000 years ago. It inhabited grasslands, woodlands and river valleys, feeding on grasses, low-growing plants and possibly roots. Its size, up to 3 meters long and weighing over a ton, meant it needed to consume large amounts of vegetation daily. But unlike most large herbivores, Glyptodon didn't need to worry much about predators. Its armour made it nearly invulnerable to attack, and its tail club could deliver devastating blows to anything that got too close. The shell, or carapace, was made of hundreds of individual bony plates called osteoderms. These plates were fused together, forming a solid, dome-shaped structure that covered the animal's back and sides. The surface was covered with polygonal patterns, giving it a textured appearance similar to a turtle shell. The shell was so strong that even the bite force of a saber-toothed cat wouldn't have been able to crack it. Some fossil shells show scratch marks from predator claws, but no successful penetrations. The tail club is one of the most impressive defensive weapons in mammalian evolution. The tail was long and muscular, with the end encased in heavy, spiked osteoderms that formed a solid mass of bone. This club could be swung with considerable force, and studies suggest it could generate enough impact to break bones or cause serious injury. Glyptodon likely used the tail club both for defense and for intraspecific combat, with males fighting each other for territory or mates. Fossil evidence shows healed fractures on some shells, suggesting violent encounters were common. The head was protected by a separate bony cap that covered the skull. This cap wasn't fused to the shell, allowing Glyptodon to move its head freely. The jaw was strong, with teeth adapted for grinding tough plant material. Unlike modern armadillos, which have simple peg-like teeth, Glyptodon had complex high-crowned teeth that could process fibrous grasses. This suggests Glyptodon was well adapted to the expanding grasslands of the Pleistocene. Movement would have been a challenge for such a heavily armoured animal. Glyptodon had short, powerful legs with broad feet adapted for supporting immense weight. It moved slowly and deliberately, more like a tortoise than a modern mammal. The shell limited flexibility, meaning Glyptodon couldn't run or climb. But in an environment with few threats, this wasn't a major disadvantage. The shell provided safety, and the tail club provided offence. Together, they made Glyptodon one of the most defensively formidable mammals ever to exist. Social behaviour in Glyptodon is difficult to determine, but fossil sites sometimes preserve multiple individuals together, suggesting they may have lived in groups. Group living would have provided additional protection, particularly for juveniles, whose shells were thinner and more vulnerable to predation. Glyptodon may have also used vocalizations or visual displays to communicate, though direct evidence of these behaviours is lacking. The extinction of Glyptodon occurred at the end of the Pleistocene, around 10,000 years ago. Climate change and the arrival of humans are both implicated. Glyptodon's armour made it safe from most predators, but it couldn't protect against human hunters armed with spears and fire. Archaeological sites show evidence of humans using Glyptodon shells as shelters, suggesting active hunting. Combined with changing habitats and shrinking food sources, these pressures were too much. Glyptodon, the walking tank of South America, disappeared. Doedicurus, the spiked wrecking ball. If Glyptodon was a tank, Doedicurus was an upgraded model with better armour and a more lethal weapon. This massive Glyptodon stood over 1.5 metres tall and stretched up to 4 metres long, weighing close to 2 tonnes. Its shell was even thicker than Glyptodon's, and its tail club was larger, heavier, and covered with vicious spikes that could impale, as well as bludgeon. Doedicurus was built for one purpose: to survive in an environment full of predators and to fight back with overwhelming force when necessary. Doedicurus lived during the Pleistocene in South America, sharing its habitat with saber-toothed cats, terror birds, and other formidable predators. The shell was its first line of defence, a massive dome of fused bone plates that covered the entire back and sides. The plates were thick, interlocking, and covered with raised bosses that made the surface extremely hard. Even the most powerful predators would have struggled to penetrate this armour. Fossils show tooth marks and scratches on some shells, but no successful breaches. The tail club was Doedicurus's signature weapon. Unlike Glyptodon's club, which was solid and rounded, Doedicurus's club was covered with long, sharp spikes that radiated outward like the head of a medieval mace. The tail could swing with tremendous force, and those spikes would have caused devastating injuries. A direct hit could break bones, puncture organs, or kill outright. This weapon wasn't just for defence. Fossil evidence shows damage on Doedicurus shells consistent with tail club strikes, suggesting these animals fought each other as well as predators. The tail itself was encased in interlocking bony rings that provided both flexibility and protection. The club at the end was formed from fused vertebrae and osteoderms, creating a solid mass of bone that could weigh over 60 kilograms. Swinging this tail required immense strength, and Doedicurus had the muscular build to deliver powerful strikes. The tail muscles are attached to reinforced vertebrae and a strong pelvis, allowing the animal to generate rotational force. Doedicurus's head was protected by a thick, bony cap similar to Glyptodon's. The jaw was powerful, with teeth adapted for grinding tough grasses. Unlike earlier Glyptodonts that may have browsed on softer vegetation, Doedicurus was well suited to the grasslands that dominated South America during the Pleistocene. Its high-crowned teeth could process abrasive plant material without wearing down quickly, allowing it to thrive in open habitats. Movement was slow but steady. Doedicurus walked on 4 short, thick legs with broad padded feet that distributed weight effectively. The heavy armour and tail club made running impossible, but Doedicurus didn't need speed. It had protection and a fence that few predators could overcome. In open grasslands where ambush was difficult and Doedicurus could see threats coming from a distance, its defensive strategy was highly effective. Social behaviour may have included group living, as with other Glyptodonts. Multiple individuals at fossil sites suggest Doedicurus may have gathered in areas with good food resources or water. Males likely fought each other using their tail clubs, with the winner gaining access to mates or territory. These battles would have been violent but often non-lethal, with most injuries consisting of shell damage rather than fatal wounds. The extinction of Doedicurus mirrors that of other South American megafauna. By 10,000 years ago, the species was gone, driven to extinction by a combination of climate change, habitat loss, and human hunting. Despite its formidable defences, Doedicurus couldn't adapt quickly enough to survive in a rapidly changing world. Megatherium, the ground sloth that stood like a bear. Megatherium was one of the largest land mammals ever, standing over 3.5 metres tall when upright and weighing up to 4 tonnes. This wasn't a tree-dwelling sloth that moved slowly through the canopy. This was a terrestrial giant that walked on its knuckles, browsed on high branches, and could rear up on its hind legs to reach vegetation that no other herbivore could access. It looked like a bear crossed with a sloth, scaled up to monstrous proportions, and given claws that could have easily disemboweled any predator foolish enough to attack. Megatherium lived across South America during the Pleistocene, from roughly 5 million to 10,000 years ago. It inhabited a range of environments, from grasslands to forests, adapting its diet based on available vegetation. Unlike modern sloths, which eat mostly leaves, Megatherium was a mixed feeder, consuming leaves, grasses, fruits, and possibly even carrion. Its versatility in diet contributed to its success and widespread distribution. The claws were massive, some reaching over 30 centimetres long. These weren't delicate tools, but powerful hooks capable of pulling down entire tree branches or digging into the ground to access roots and tubers. The claws were so large that Megatherium couldn't walk flat-footed. Instead, it walked on the sides of its feet and on its knuckles, much like modern gorillas. This odd gait protected the claws from wear while still allowing effective movement. The ability to stand upright was one of Megatherium's most distinctive traits. Its hind legs were thick and muscular, and its tail was strong enough to act as a third support point, forming a tripod. When Megatherium rose on its hind legs, it could reach vegetation 6 metres off the ground, higher than any other Pleistocene herbivore. This feeding strategy allowed it to access resources others couldn't, reducing competition and increasing survival chances. The teeth were simple pegs without enamel, suited for grinding plant material. Unlike many herbivores that have complex molars with ridges and valleys, Megatherium's teeth were smooth and grew continuously throughout its life. This suggests a diet of relatively soft vegetation that didn't require extensive chewing. The jaw muscles were powerful enough to process large volumes of food efficiently. Despite its size and formidable claws, Megatherium was probably a gentle giant most of the time. It likely spent its days browsing peacefully, using its height and reach to gather food without much effort. But if threatened, those claws could become deadly weapons. A single swipe could inflict serious damage, and the sheer size of the animal would have made most predators think twice before attacking. Only the largest saber-toothed cats would have dared to hunt Megatherium, and even then, only juveniles or sick individuals would have been viable targets. The extinction of Megatherium at the end of the Pleistocene remains debated, but human activity likely played a significant role. Archaeological evidence shows humans hunted ground sloths, and the timing of Megatherium's disappearance closely follows human arrival in South America. Climate change also contributed, as shifting habitats reduced the availability of the mixed vegetation Megatherium depended on.